So today we're going to start looking at unsupervised learning. We're going to look at some things like feature selection that can be applied both to supervised and unsupervised learning. But then the second part of the semester will focus on unsupervised learning, and I'm going to start with the introduction to those types of problems. So for this first hour, I'll give a brief introduction to unsupervised learning and contrast it with what we have been doing with supervised learning previously. And then I'm going to focus on some side issues like visualizing data in multi-dimensions and also feature selection. So these are not strictly for unsupervised learning. They can be applied to supervised learning problems too. But since they are not peculiar to supervised learning, they fit here in this transition between the two kinds of problems. So the basic idea with unsupervised learning is that we are not trying to fit some target values that we want to predict, either with classification or regression. So we don't have those data labels that we always use in supervised learning problems, where we have that y value that we want to predict, and then we adjust the parameters of our model by trying to minimize the error between the prediction and the target value. So instead of doing that, what we have is a learning system that is trying to find new values, new ways of describing the data. So we don't have this error measure or this trying to adjust parameters to predict something, but we want to transform the features that we have in a way that is more informative. Now, there are many examples here. We're going to see a few aspects of this problem in feature extraction in the second hour. Also, we can think a bit about feature selection as sometimes a problem of unsupervised learning, depending on how we do it. But the basic idea is that instead of trying to create something that predicts a value, we are trying to transform the data into something that is more informative. Now, the idea that we are learning without having a target value that we want to adjust that we want to predict, doesn't mean that the data cannot be labeled. We can use unsupervised learning in conjunction with supervised learning, for example, for pre-processing data or simplifying data, something like that. It just means that for unsupervised learning, we are not worried about trying to predict some known values. Some tasks that we can apply unsupervised learning to is, for example, trying to understand data. So if we can select the right features or visualize data in an appropriate manner, it can help us understand the structure of the data. We can use unsupervised learning for density or distribution estimates. We already saw that with kernel density estimation, which is unsupervised learning, and we can use those models to obtain an estimate of the probability density of some values, for example. We can do feature extraction, feature selection with unsupervised learning, and also a major focus in this course will be for a few lectures, clustering, which is trying to group together examples that are similar and separate them from examples that are dissimilar to those others. Clustering is very useful to understand the structure of the data, because then we can see within our data set what kinds of examples we have. So if you want, one way of thinking about clustering is to think about a classification problem, but where the classes are not given to us explicitly. We cannot observe the classes, but rather are some variables in the model, so some parameters in the model that assign examples to different groups. In this lecture, we're going to look at visualizing data and selecting features. So first, let's go back to this data set, the iris data set, which has these three classes for the different species of iris flowers. We have setosa, versicolor, and virginica, and also we have 4 attributes to describe each flower: the length and width of the sepals and the petals. So this gives us a set of data that is four-dimensional, and it's not easy to represent data in four dimensions. So we need some ways of looking at the data that can overcome the problems of representing features in four dimensions. For these examples, I'm going to use Pandas, this Python for data analysis library. You have this installed in Anaconda. Going into detail on how to use Pandas is outside the scope of this course, but it's a useful library when you're dealing with data in tables, where you can access data by the names of the columns, you can cross tables and so on, and also has lots of utilities that serve as a wrapper for PyPlot for doing specific plots. So if you want to work with data, trying to understand data, processing data, cleaning up and so on, using different tables and joining them together, then this library is very useful. So I'm going to use this to show some visualization tricks, techniques with the iris data file. So we have this CSV data file. The first row is the names of the columns. Then we have the values here, the features. We also have a class there, but we're not going to worry too much about the class. We're not concerned with trying to predict the class of the flowers. We're going to try to visualize the data set. So we have in the Pandas library, we have this read CSV function that returns data frames. This is an object that we can use to access data. If you have experience with R, this is very similar to data frames in R. Otherwise, this is basically an object that you can think of it as an extension of the NumPy matrix to tables like you use in worksheets or things like that. So you have column headers, you have the rows, you can select subsets of the table and so forth. So one of the things this data frame object has is the ability to plot the data. You can use the plot method. You specify what kind of plot we want. So we want a histogram, the number of bins, and this alpha is the opacity of the drawing. So if you use an alpha of 1, then the items represented are not transparent, and if they overlap, then the ones that are painted after will cover the ones before. But if you use a fraction, they will be semi-transparent, and we can see the result like this. So we have the different attributes, and these are the histograms for the attributes. So here we can see the distribution of the different attributes. For example, sepal length, petal length, and then the width here. And there is some transparency in the columns because we use that alpha value. So this would be one way of looking at the different features. We have no information on how they are correlated, but we are looking at the different distributions. We can also do a histogram with the features separated. So instead of using plot of histogram type, we use the hist method here. So basically it's the same thing, but now it will represent each feature separately. So you can do these kinds of things with PyPlot. You can do multiple plots in the same figure and so on. But Pandas has the advantage that it wraps those more basic functions and can do this easily. So with histograms or kernel density estimation, we can look at any number of features, and we have an idea of the distribution of each feature. One drawback of this is that we do not know how the features are correlated. So we can look at that. We'll see some solutions for trying to visualize those correlations. But another way of looking at individual distributions, this kind of thing, histograms, is okay if you have a few features. As you start having more and more, then it starts to become difficult to compare them visually. And one useful representation is the box plot. So the box plot represents the median value for each series of values with this line. Then you have the quartiles here. So this is between the 25% and 75%. So half of the points are inside this box. Then we have these whiskers there, which go starting from the first quartile or the third quartile, depending on whether you go low or up. They go all the way to the same distance multiplied by a factor. This can be configured, but usually they go up from the third quartile or down from the first quartile, a function of the size, the distance between these two quartiles here, or they stop at the maximum or the minimum value. So this means this is actually the minimum value, so the whiskers here are fairly close to the quartile. If we have values that fall outside the whiskers, then they are plotted as outliers individually. So in this case, we can see that for sepal width, most of the values are very close together here. So we have this 50% region where half the values is very narrow. But then we have some outliers outside of these whiskers. We can see that with petal length, the opposite happens. We have a very broad distribution, even between these two quartiles, but then we don't have outliers outside that region. So this is a way of a simplified representation that makes it easy to understand the distribution without all the complication of the histogram, and it makes it easier to compare different distributions, even if you have many of them. Now, all of these kinds of plots give us the distribution of individual features, but they do not give us information about how the features are related. We can get some information about that with this scatter matrix plot. So the idea of a scatter matrix plot is that we plot in the diagonal usually the distribution of each feature, and off the diagonal a plot of one feature versus the other. So here, for example, we have sepal width plotted against sepal length. Here, petal length plotted against sepal length, and so on. This is easy to do with Matplotlib, with pandas too, because you have this scatter matrix function. So you just give it the data, and you can specify what you want in the diagonal, if you want histograms or kernel density estimation, and it automatically does all these plots. You could also do this with loops and pyplots, but it's easier to just use these functions in pandas. So in this case, we can both see the distribution of each individual feature, either in kernel density estimation or histogram. We can choose, but we can also see, for example, that petal length and petal width are very strongly correlated. We see here in diagonal they are proportional to each other, so we can see these correlations. On the other hand, for example, sepal width and sepal length don't seem to be strongly correlated here. So this not only gives us information about the distribution of the features, but also about how they correlate in pairs. We cannot see correlation of all of them at the same time, but at least in pairs we can see how they correlate. Now, one way of trying to look at the relation between all the features in a multidimensional data set is to use parallel coordinates. When we plot like this, we use perpendicular axes. So we can do a two-dimensional plot with two axes, and we plot as points each example in those coordinates. But this is limited to 2 dimensions. If we go to 3 dimensions, we can still do some projections, but more than 3 dimensions, we cannot even imagine what the plot would be like. With parallel coordinates, we draw the axes in parallel. So in this case, we have 4 features. We have the sepal length here, sepal width, petal length, and petal width. So we have 4 parallel axes. But now, each example is no longer a point, it's a line connecting the values for its features. So we can color it, for example, according to the class. If we do that, it's easy to see that the 3 types of flowers have different combinations of values. So we see here in red Setosa, in green versicolor, and in blue Virginica. So this way we can represent multidimensional data, but each example is no longer a point, it's a set of lines that joins the values of the different features. And these different features are drawn in these parallel axes, and we can have as many as we need. So to do this, we can use the parallel coordinates function. It's also available in pandas, so we can give the data. If we don't have classes, we can just look at the structure of the data. So just by looking at this plot, it's easy to see that we have at least two types of examples in our data, because it's clear that these lines are different from those. If you have classes in your data, you can also specify the different colors for the different classes. So in this case, I just used red, green, and blue, and this can help us see the differences. So for example, in this case, versicolor and virginica are not very obviously different because they overlap a bit. But if we plot the colors, we can see that they are easy to distinguish here. So this is a way of representing multidimensional data, which we cannot plot with the regular Cartesian coordinates, because that only works well for 2 dimensions. But if instead of points we draw lines, we can represent examples differently, like this. There are also some properties of these parallel coordinates, depending on how correlated the features are and so on. So parallel coordinates have some specific geometry properties that can be useful. We're not going to go into those details, but there are also variants of this kind of representation. For example, Andrews curves is also a representation for multidimensional data, where we draw each example as a line, but in this case it's a sinusoidal line, so with sine and cosine summed up, and for each feature we have one different frequency. So we suppose that we have these features, feature 1, 2, 3, 4, 5, and so on. Feature 1 determines the height of the curve, so it's this constant here. Then feature 2 will be multiplied by a sine of period tau, feature 3 by the cosine of period tau, then feature 4 by the sine of 2 tau, and so on. So depending on the magnitude of these features, different frequencies will have higher or lower values, and we get a result something like this. So you can see here also the difference between the 3 kinds of flowers, and you see that they are different in height here, in the position of the curves. This is determined by the first feature, and then we have the different contributions of the different frequencies depending on the different features. So by representing each example as a line, either with the Andrews curves or parallel coordinates, we can more easily see the relation between the different features and the kinds of examples that we have in our data. Another way of visualizing multidimensional data is this RADVIS. So in this case, we are using the different axes by spreading them radially around the circle. So we have all the different features as different axes in this circle. In this case, we have 4 features. If we had 5 features, then we would have 5 uniformly spaced attractors there, and so on. And now we represent each example as one point, but the point is being pulled by the different features. So depending on the relative intensity of the different feature values, it will be placed in a different position in the circle. So points that are even in all the features, so they have the same value or similar values over all the features, get more to the center. Points that have one feature that with larger values get drawn in that direction. If they are 2 features, then they will be in the middle, and so on. So this is also useful to spread out the points depending on the relation between the features. So the basic problem here is that when we have data with more than 2 dimensions, then visualization becomes hard. With 3 dimensions, it's just a matter of projecting them, the data adequately, but we can still think in 3 dimensions. With more than 3 dimensions, then we cannot even imagine how the data would spread out, so we need different techniques for trying to understand the structure of the data. So one way is to look at distributions, but we also need to understand how the features are related. We can easily do pairwise plots because then we are reducing the problem to a set of 2-dimensional plots. But this does not give us all the information because we are only looking at correlations between two features at one time. With parallel coordinates or Andrews curves or Radbis and so on, we try to represent examples in all the dimensions at the same time. So this is one thing. We're not going to focus too much on this because this now will depend a lot on the particular problem and how we're trying to understand the data. But it's just to call your attention to these kind of techniques that in practical problems are very useful, because the first step usually to applying some machine learning methods is to really understand the data that you have so you can evaluate what is more adequate to deal with that data. Okay, another problem that we didn't look at so far is what to do when not all the features are equally useful. Because sometimes what we do is we don't have necessarily the best features for solving some problem. We just have whatever features happen to be available because that was the data that was collected, it's what we can use and so forth. Sometimes we can have too many features for available data, or we can have features that are really not useful for solving our problems. So, for example, if we are dealing with supervised learning, any feature that is not informative about what we're trying to predict, we don't need to use it. Another question that sometimes arises is this decision about whether or not features are worth measuring. For example, if you are dealing with problems of diagnosing diseases or something like that, there are features that are easy to acquire, for example, the patient's age, gender, and so forth. There are other features like that may require drawing blood and doing some expensive tests and things like that. So we may need to evaluate how useful the feature is in order to decide whether or not we need to obtain that feature. So, and there's also the problem that sometimes we have smaller data sets but too many features. So even if we have a very simple model, the mere fact that we have too many features will already lead to overfitting, because then we can adjust to any detail in the features, and we get problems in trying to predict anything. This is also a concern in unsupervised learning, not only in supervised learning, because for things like clustering and so on, dealing with high-dimensional data can give us some problems. We'll see more about that in future lectures. So basically what we want to do is to reduce the number of dimensions in our data set, the number of features, and one way of doing that is picking the best features. So the question now is to figure out what are the best features. How can we find the best features? Okay? So let's go back a bit and think about supervised learning, and we can try to think of how each feature correlates to whatever we're trying to predict, for example, the class. So one simple test could be this chi-square test, where imagine that we have categorical features, and so we can measure the frequency of each value in a feature. We can, if the feature is not correlated with the class, then we expect that the fraction of the examples that have that particular value will be on average the same for all the classes. So usually the same for all the classes, and we can have this expected frequency over all the classes. But now we can measure for each class what is the frequency of that value. If the deviation is merely at random, so they have the same distribution, but it happened that there was some deviation by chance, then this should be distributed with a chi-square distribution, and so we can do a null hypothesis test. So if the likelihood is high enough, we cannot reject the possibility that the feature has nothing to do with the class and the differences are just at random. However, if the differences are too much and the likelihood becomes too low, then we can reject that hypothesis. And in that case, we find a useful feature, because then we cannot say that it's by chance that this feature has different values in some classes and in others, and so we can use that information to try to predict the class. So a more familiar, a bit more sophisticated test, which you probably know, analysis of variance, we can consider that the variance between the different groups and the variance within the groups with this appropriate scaling has a distribution, this F distribution, with if there is no difference between the groups in those features. So if all the observed differences are due to sampling, to the randomness of our sample. Please. Mm-hmm. So the question was, if we only need to test each feature individually, or if we need also to see how they correlate. And yes, we also need to see how they correlate and combinations of features. So I'm starting with this univariate filter, and then we'll see how we can do that for combinations of features. But this would be the basic problem, mostly in supervised learning, where we want to select features by their how much information they give us about what we're trying to predict. So in this case, if the likelihood of this is high enough, it's within what is expected by this F distribution, then we cannot reject the null hypothesis that our feature is making no difference between the different groups. However, if we get a very low probability here or a very high value for this fraction, so the variance between the groups is much larger than expected when compared to the variance within the groups, then we have found a feature that is very informative about the different classes that we're trying to predict. So if we want to do this analysis of variance, or this F-test, with scikit-learn, we have this F plus this method that we can use to compute those values for the F distribution, so these fractions here, and the corresponding probabilities of having those values are higher if the null hypothesis is true. That is, the probability of this happening if there is no difference between the groups and it's happening just by chance. So this is an example with our iris data set. We can compute the F values and the probability with the F classify by inputting the features and the class labels. So it's going to compare the different groups according to the class labels. This is mostly used in supervised learning, although we can select features and then do clustering and so on. We don't need to just use this for supervised learning. But it gives us the F values. Here are the F values, 119, 47, and so on. And these are the probabilities with the F distribution of these values. So you see they are very low, minus 31, 10 raised to the minus 31, minus 16, and then these two, minus 91 and minus 85. So if we wanted to select the features that have the strongest correlation with the class labels, we would select those that have the lowest probabilities here, or the higher F values, because these ones are the ones that deviate more strongly from what would be expected if there was no relation between feature and class. So in this case, we could select these last two, which is the length and width of the sepals, I think, and we get this plot here. Now here we can see, we can start to suspect that maybe this wasn't the best choice, because it's related to your question. We can see that individually each of them is strongly correlated to the class, and we can see that in the plot because we have one class here, then another class here, and another here, and the same in the vertical axis. But we can also see that they are very correlated one to the other. So basically, one of these features is giving us a lot of information, but the second one is giving us the same information as the first, or nearly the same, so they are not, maybe they are not very useful together. So if you want to do univariate filtering, looking at each individual feature, with scikit-learn, you have this feature selection module. You can do this select k-best, so this is to select the k-best features. You can use one measure for selecting the best. So for example, the F-test for classification. There is also a test for regression, but in this case we're using for classification. And so we use the select k-best with this measure, and k equal 2. This means that we want to select the 2 best features from that data set. And then this fit transform method does the fit first. It computes which are the best features, and the transform in this case will transform our original data into a reduced data set of features, so a reduced set of features with only the 2 best features. So if you want to do univariate filtering, you can decide which criteria to use, which scoring function, and then use this class to prune down your data set to only the features that are most useful. So basically, for univariate filtering, we are trying to compare each attribute to the predicted, whatever value we want to predict. So this is mostly in the context of supervised learning, although we can then use the selected features for clustering, for anything else. Okay? But we need the target values for this kind of selection. There are many different measures. We can measure correlation directly, or mutual information, and so on. But in any case, the idea is to try to select each feature according to how much it can tell us about what we're trying to predict. So features that are more informative, we want to select those. We can also do this with model-based ranking by selecting a feature and then trying to train some model with that feature in order to predict whatever we want to predict, and select those that work best individually. But we'll see this better because this kind of wrapper methods can be more generally used to test combinations of features. So another thing that we can look at is how to choose sets of features. So this would be multivariate filtering, and it's filtering because we are doing this before actually starting to train anything. So ideally, we want features that are relevant, that is, they give us information about what we want to know, but we do not want features that are redundant. We don't want a feature that is telling us the same thing as another feature that we already have, because in that case, we only need one and not the 2 of them. So this is one thing that we can also look at, which is correlations with another feature. This would be an example where we have a high correlation between the 2 features. So instead of picking these 2, we could pick one of them and then go for one of the others that was not so good individually, but would probably be a best fit together with one of these. But we can go, we don't need to just look at 2 different features. We can generalize this. And this is usually what's done with wrapper methods. So we use some scoring algorithm that usually is the same machine learning algorithm we want to apply in the end. So for example, if you are dealing with a classification problem, you can use the same model, but for a subset, or the same kind of classifier, but for a subset of features, and then search through different subsets of features until you find the ones that give you the best cross-validation error or something like that. So this is the idea of scoring the performance of a set of features, usually by a machine learning algorithm, and then having a search algorithm that will go through different combination of features until we find the best set of features. So the best set of features in this case is actually measured by the performance of the algorithm, and that's why usually we use the same machine learning algorithm that we want to use in the end. So the problem now here becomes how do we select which features, because this is a combinatorial problem. If you have a large number of features, you can either include or not each of the features. So this gives you 2 raised to the number of features, a different combination. So it quickly explodes if you have a large number of features. So one way of doing this is with deterministic wrappers that will go exhaustively through all the features and run a path through all those combinations. So for example, this sequential forward selection, you start with one feature, you test one feature, and then the second one, the third, so only one at a time, and you check out of all the features which one performs best individually, without any other. Then you keep that one, and now you're going to test each of the other ones in combination to the first one, and then you repeat each of the other ones in combination with the first 2, and so forth. So this is a greedy algorithm where you keep always the best features so far. Usually you do this until you no longer have an improvement in the performance, because at some point you can start finding features that are no longer relevant, and so they do not improve the performance. Or if you reach a number of features that you decide it's okay. So if you're doing things like cross-validation and so on, usually if you don't have a lot of data, you can even have to stop very early, because the more features you have, the more overfitting you'll have in your model. Okay? So this generally the idea is we're going to test all of the features individually, then all of the features along with the best one in the first round, then all of the remaining features along with the best 2 in the first 2 rounds, and so forth. We can also do this the other way around. We can start with all the features and then try what happens if we remove one of them or another of them and so on, and see which is the best one to remove. That is, which is the less useful feature of the set. And then after removing that, we repeat with the same, with the set of features that we have, and we keep removing until we either reach a desired number of features, or we no longer see any improvement, or the loss is sufficiently small, or something like that. So basically, the choice between the two depends on how distant you estimate your target is. So if you have a large number of features, and you want only a small subset of those features, it's best to go with the forward selection, because you start with 1, 2, and so on, and stop fairly soon. If you want to keep a substantial fraction of your features, then it's best to start with all of them and just throw away the ones that are not very good. If you have a very large set, and this would take a long time to go through all these combinations, or if you have a large set, you have a problem that these two methods actually only go through a very small path, a very small number of combinations out of the whole possible number of combinations. You can try a non-deterministic algorithm to sample the different combinations. So this can be things like simulated annealing, genetic algorithms, Monte Carlo, something like that, where you basically are drawing non-deterministically sets of features and trying to find out which combinations work best. Then there is another way of doing feature selection, which can be part of the algorithm itself. Yeah?
You said previously that when we have a lot of features, we can offer a number of features.
Mm-hmm.
But if we extend the sample size, that problem won't happen.
Yes, in theory, if you increase the size of your data sample enough, you can solve overfitting problems. The problem here is that, in general, you cannot just increase the sample size, because the data is what you have, and that's fixed.
But my question is, like, if we could do like a bootstrap to increase the sample.
You cannot use bootstrapping to increase the data, because what you can do with bootstrapping is to simulate drawing another sample of your data. But note that in bootstrapping you are drawing examples from the data that you have. So if you just create a replica by bootstrapping and you join the two together, you don't get twice the number of examples. You just get copies of your original examples. So you don't have extra information there. So bootstrapping allows you to estimate some statistics on your model by simulating what would happen to your model if your data was slightly different but drawn from the same distribution. But it doesn't really give you more data points. It's just, you're just using different combinations of data points.
Okay, so even with the bootstrap, we get the same problem with overfitting.
Yes, you would still get overfitting because you have the same data points. Just because you're repeating them, it wouldn't make a difference there. There are some similar approaches to solving problems of class imbalance and so on, but they are always very limited to the data that we have. So in general, in theory, the solution of increasing the size of the data would work. In practice, we don't have that luxury, so we only have the data that's available. So this basically, for wrapper model, for wrapper feature selection, we are using machine learning algorithms to test different combinations of features and see which combinations perform better. We can also do embedded feature selection for some specific machine learning algorithms that automatically select features. For example, decision trees will look at one feature at a time to try to separate the data, and so we'll place the more useful features higher up in the tree or in the first branches, and leave the less useful features for later on. So the decision trees are a way of doing embedded feature selection because they automatically choose which are the best features. Naive Bayes can also be done with by weighting features differently according to how much information they are giving us, and so can be used for embedded feature selection. And there are also some regularization methods. We saw as an example of regularization the L2 norm, which was to add as a penalty to the cost function the sum of the squares of the size of our parameters. This tends to make the vector of parameters small, but not zero in any of the directions, just the overall size small. Another way of doing regularization is with the L1 norm. So this is the sum of the modulus of all the parameters, and this tends to make some parameters go to zero if they correspond to features that are not very useful. So if you do, for example, logistic regression with the L1 norm, you'll see that features that are not useful will tend to have zero weights on the final vector for the decision surface, and in that case you can identify which features are not being used there for classification. So this is embedded feature selection, is when we use some properties of some machine learning algorithms that can automatically select the best features. So basically the problem here is that we want to discard features that are not particularly useful. We want to reduce the dimensionality of our data, and we can do this by filtering. So first, before we start using machine learning, we can try to throw away some of the features, either because they individually are not very correlated with what we want to predict, or because they are too correlated to each other, so we can throw away one of them and keep the other and still retain the same information. We can also use machine learning algorithms to test different combinations of features. So we are looking at subsets of our features to see which combinations work best. Or we can use machine learning algorithms that do feature selection as part of the way of optimizing the parameters. So to sum up, we saw the idea of unsupervised learning. We're going to look at more examples, especially clustering in the next weeks. But the idea here is that we are not trying to, we are not aiming at something that we have already observed and try to adjust to that. We are trying to find some information about the structure of the data. And we saw some related problems here with visualizing data and selecting features. So in some cases, this can be related to supervised learning, where we actually have a target value and are looking at correlations. But these problems of using wrapper methods and so on are more generic than just for supervised learning, and can also be used for feature selection in unsupervised learning. So if you want to see more about this, there are some references here in Alpython, but also you can look at a visualization tutorial in Pandas. This is easy to find online. And it gives you lots of examples of different ways of plotting data. So this is good for data understanding when you're dealing with data that you don't know very well. It's useful to look at it this way. You also have a feature selection tutorial in scikit-learn, and this kind of taxonomy for feature selections, filter, wrapper, and embedded. I took it from this paper on filter selection techniques in bioinformatics, and so if you want more details, you can look that paper up.